All right, so today we're going to go over the coin problem, which is a common dynamic programming problem. First, we should understand what exactly dynamic programming is. So, the definition of dynamic programming is an algorithmic technique for solving complex problems by breaking them down into simpler, overlapping subproblems and storing, otherwise known as memoizing, their solutions to avoid having to do redundant work and avoid having to use redundant time complexity. The key properties of memoization is an optimal substructure, which just means that an optimal solution to the problem can be composed from an optimal solutions to its subproblems. So dynamic programming is the most optimal way to find a solution. Additionally, another key property is overlapping subproblems, which just means that the problem can be broken into subproblems that recur multiple times, very similar to the structure of recursion. There's multiple approaches for dynamic programming, but today we're going to use top-down, otherwise known as memoization, and this is just recursively solving subproblems and caching their results. In the case scenario of the coin problem, we're not necessarily using recursion. We're rather using a nested loop structure today, but it's the same idea. It's really similar to the same idea of how recursively you break it down into smaller and smaller and smaller subproblems and build your current solution off of previous solutions from your subproblems. So the question today is consider a money system consisting of n coins. Each coin has a positive integer value, and your task is to calculate the number of distinct ways you can produce a money sum x using the available coins. So for example, if the coins are 2, 3, and 5 and the desired sum is 9, there are 8 ways to create this sum. And these are simply just the different permutations of these three numbers that create a sum of 9. So we're given an array of coins and a desired sum, and we have to find how many ways these coins can, how many permutations of these coins sum to our desired sum, in this case scenario 9. So first we have to understand how we can approach this problem using dynamic programming. So given an array of integers representing the values of coins and a desired sum x, we can create a 1D memoization table of size x plus 1, where memo of x stores the number of combinations of coins that sum to x. So for example, if these are our coins and this is our sum, we create a memoization table of size 10, which is just one more than what our sum is. Memo of 0 is equivalent to the coin combinations that sum to 0. Memo of 1 is equivalent to the coin combinations that sum to 1, etc. And then finally, memo of x or memo of 9 is the coin combinations that sum to x. And this means that at the end of our nested loops and after everything completes, that memo of x is going to store our final answer. All right, so first we have to figure out what the recurrence relation is for this memoization problem. So the base case is memo of 0 equals 1, and this is because there's exactly one combination of the coins 2, 3, 5 that sum to 0, and that is simply just the empty set or none of the coins. Now, for each sum 1, 2, all the way to sum of x, our recurrence relation is going to be memo of I equals memo of I plus memo of I minus coin. Typically, whenever you're solving this problem, you don't need this mod. This is just how our problem in homework 7 instructed us to do it. It instructed us to store the solution modded by a certain value. Why does this make sense? You build up from a smaller sums. Whenever you add coin C to a valid solution for S minus C, you get a new solution for S. So just for example, and we'll trace through this, but if you're trying to create a sum of 5 and you are currently on a coin 3, if you know that memo of 2 has a value of 1, which means that something sums to 2, if we're currently on our coin 3, then we know for a fact that if memo of 2 is equal to 1, that we can simply just add the value of memo of 2 to our current value 3 because 3 plus 2 equals 5. And that's the idea of how memoization works throughout this problem. So now we're going to trace through it. First, we're tracing through it for a sum of 1, which is our first iteration of our outer loop. This is a portion of the code. We'll go through the entire code at the end, but this is just the structure that updates the memoization table. So our outer loop is looping through all of our possible sums, so 1 through 9. Notice how we're not starting at 0 right here because we already declared 0 as our base case where memo of 0 equals 1. Therefore, we don't need to process it again. And our nested loop is simply just looping through all of the coins. So thinking about it, we're looping through all of the coins for every possible sum in our memoization table. So for iteration 1, when sum equals 1, which is our outer loop value, our nested loop value is 2 because we're on coin of 2 first. Our if case is not met because 1 minus 2 is not greater than or equal to 0. Similarly, for our second iteration of our nested loop for sum equals 1, the if case is not met for 3 either because 1 minus 3 is also not greater than 0. And again, for our third iteration of our nested loop for sum equals 1, for the coin 5, this if case is not met. Therefore, for sum of 1, there's no possible ways to create a sum of 1 from these given coins right here. So after iteration 1, our memoization table looks like this, where memo of 1 is equal to 0. And this is because with the coins 2, 3, 5, we did not find any possible way to create a sum of 1. Therefore, memo of 1 is equivalent to 0. So now we're going to trace through our second iteration, or sum equals 2. So on iteration 2, we're now on sum equals 2, which is the value of our outer loop, and we're on our first iteration of our nested loop, where coin equals 2. Our if condition is met this time because 2 minus 2 is greater than or equal to 0. Therefore, we update memo of 2 to be equal to 1. In this case scenario, memo of 2 is updated to 1 simply just because we can create a sum of 2 with the coin 2 itself. In that iteration for coins 3 and 5, the if condition was not met because 2 minus 3 is not greater than 0 and 2 minus 5 is not greater than 0. Therefore, the if condition was only met for the coin 2. And after our second iteration for sum of 2, our memoization table looks like this, where memo of 2 is equal to 1. This is because with the coins 2, 3, 5, it's only possible to create a sum of 2 with the coin 2 itself. So that's what represents the 1 right here in memo of 2. So now we're going to trace through our third iteration of our outer loop, or sum equals 3. So now we're on sum equals 3, which is the value of our outer loop, and we're on coin equals 2, which is the first iteration of our nested loop right here. So we do meet the if condition where 3 minus 2 is greater than or equal to 0, but despite meeting that if condition, memo of 3 still remains 0. And this is because although the if condition is met for coin 2, memo of 3 is updated to 0. And this is because memo of 1 is 0. So just thinking about it, we're trying to create a sum of 3 right now, and we currently are on a coin 2. If we're currently on a coin 2, then the only way that we could create a sum of 3 is if we had something that summed to 1, because the only way to create 3 from 2 is 2 plus 1. But since, as we can see right here, memo of 1 is 0, that's why memo of 3 is 0, because with the coin 2, there's no way that we could sum to 1. Therefore, there's also no way that we can sum to 3 with the coin 2, because the only way that we could do that is if there was a sum of 1. So although the if condition was met here, the memoization table is not updated to a value greater than 0. So now when we're on our second iteration of our nested loop for the sum equals 3, or 3, we meet the if condition and we update our memoization table to be equal to 1. And this is simply just because we can create a sum of 3 just from the coin 3 itself. For coin 5, the if condition is not met because obviously 3 minus 5 is not greater than or equal to 0. So after iteration 3, our memoization table looks like this, where memo of 3 is updated to 1. And this is because with the coins 2, 3, and 5, it's only possible to create a sum of 3 with the coin 3 itself. All right, so now we're going to trace through sum of 4, so our fourth iteration. So our summation is 4, which is our outer loop value, and we're on our first iteration of our nested loop, which is coin 2 right here. So we meet the if case, 4 minus 2 is greater than or equal to 0. So in this case scenario, this is really our first instance of memoization in action and seeing how it works. We're updating memo of 4 to be equal to 1. And this is because we're currently on coin 2 and we're trying to get a desired sum of 4. We know for a fact that memo of 2, as we can see right here, has been filled with a value of 1, meaning that we know for a fact that there's one way to create a value of 2 from these coins, which is just the coin 2 itself. Since we know for a fact that there's a way to create 2, we also know for a fact that there's a way to create 4 because we can simply just do 2 plus 2. And that's why in this case scenario, this is why our recurrence relation for our memoization table works, because we're basically saying memo of 4 equals memo of 4 plus memo of 2. Memo of 4 was 0, and memo of 2 was 1. So we change memo of 4 to be equal to 1 because we know for a fact that if something sums to 2, then we can simply just multiply that by 2 to add it to 4. Therefore, since memo of 2 is equal to 1, we can in turn make memo of 4 equal to 1 because we can simply just do 2 plus 2 to get our desired sum of 4. And like I said, this is really our first instance of memoization in action in this problem. For iteration 4, for the coins 3 and 5, the memoization table did not get updated. That's because for 3, there was memo of 1 is 0, so there was no way to get a summation of 4 from 3. And 4 minus 5 did not meet the if condition. So after our fourth iteration of our outer loop where the summation equals 4, our memoization table looks like this, where memo of 4 has been updated to 1. This is because with the coins 2, 3, and 5, it's only possible to create a sum of 4 with the coin 2 plus itself. So now we're on iteration 5, or where our summation equals 5, and our outer loop value is 5, our nested loop value is 2. We're on our first iteration of our nested loop. We meet the if case, so we update memo of 5 to be equal to 1. And this is another instance of memoization in action. So we're trying to get a summation of 5. We currently have a coin 2. If we currently have a coin 2 and we're trying to get a summation of 5, that means that we need a value of 3 because 2 plus 3 is equal to 5. Looking at our memoization table, we can see that memo of 3 is equal to 1, which means that something in the coin sums to 3. In this case, it was just 3 itself. Since we're trying to get a sum of 5 and we're currently on the coin 2, since we know for a fact that memo of 3 is equal to 1, we can in turn make memo of 5 equal to 1 because we can just do 2 plus 3. Similarly, just the backwards, now we're on coin 3, which is the second iteration of our nested loop. And this also meets our if condition. And now we can update memo of 5 to be equal to 2. That's because we previously just discovered that we could add 2 plus 3 to get 5. And now, since we're on coin 3, we know for a fact that we can get a summation of 5 if memo of 2, if memo of 2 is not 0. So we can see that memo of 2 right here in our memoization table is 1. Since we're on 3, we know that 3 plus 2 is equal to 5. So since memo of 2 is equal to 1, we can now update memo of 5 to be equal to 2 because we've now found two ways to create a summation of 5 with 2 and 3. And on the third iteration of our nested loop for a summation of 5, we also update our memoization table again. And this is simply just because we can create a summation of 5 with the coin 5 itself. So after iteration 5 for sum equals 5, memo of 5 is equal to 3 right here. And this is because with the coins 2, 3, and 5, it's possible to create a sum of 5 by doing 2 plus 3, 3 plus 2, and 5 itself. Now, this same process goes for sum 6, 7, 8, and 9. And because of the properties of memoization, memo of x is going, or memo of 9 in this case scenario, is going to hold the solution to our problem at the end of our nested loops. This is because memo of 9 holds the total number of combinations of coins that sum to 9. Just like how we went through memo of 5, we know that there's 3 possible combinations of coins that sum to 5, as we can see right here in our memoization table. When we continue working through our memoization tracing, we come up with 8 different possible solutions for a sum of 9, which are listed out right here, which is simply just the different permutations of these 3 numbers that sum to 9. So this is the full solution in code. So this solution is in C++, but essentially we just made a memoization table of size x plus 1. As we stated in the beginning slides, we made memo of 0 equal to 1 because that is our base case, obviously because we can create a sum of 0 from just having an empty set, none of the coins. So that's why memo of 0 is equal to 1 right here. Then we have our nested loop structure that we've been working with through the past slides and our recurrence relation right here. And as I said, at the end of our nested loops, once everything completes, memo of x is going to hold our desired solution. Therefore, for the final solution of this problem, this is the method called num combos to sum. And we simply just return memo of x because that is going to hold the number of permutations that create the desired sum that we're looking for.